In this video, I'm finally going to do what I promised to do in the first video on functions, I'm actually going to give you a formal definition of functions. So first thing we're going to do before we have a formal definition is we have to interpret our function as a set of ordered pairs. And then we're going to use ordered pairs to give a formal definition of functions. So here's one of our friends that keeps following us around, our old function friend. F of x equals x squared, where the domain and codomain are the real numbers. Now, one way of expressing this function is as a graph. And so, you've seen this graph before. This is nothing terribly surprising to you. But the important thing to notice about this is the graph of the function f consists on points on a plane, right? Like that one. So there's the little black dot there. That's one of the points on the graph. And those can be thought of as ordered pairs because it has an x-coordinate and a y-coordinate. And so that particular one, it's kind of hard to see the numbers. It's a little bit small, but the x-coordinate is 2, the y-coordinate is 4, and so that is the point 2, 4. And every point on the graph has an x-coordinate and a y-coordinate, and the x-coordinate of the points on the graph, well, that is going to be the input of the function. Those are our x's. The y-coordinates of our graph, those are going to be the output that goes along with the given input. So we can actually think of a function this way, not a function being expressed as a graph, but a function being ordered pairs on the graph. So we can actually define the function as a set of ordered pairs. And it doesn't have to be just a Cartesian plane type of thing, right? So that one, the inputs and outputs were both real numbers. We can do any function from any set to any other set. So let me see, what would an ordered pair xy for the function f, what would that even mean? Well, remember, we think of our x-coordinate as an input, and the inputs to our function f, those are elements of A. So x is going to be some element of A. And the y-coordinates, those are outputs, right? So y, first of all, y is equal to f of x. So it's not just any old output, it's the output for the x-coordinate. But also, since it's an output, it also has to be in the codomain B. Which means that if we want to look at where to find the ordered pair xy, it is going to be in the Cartesian product of A and B, A cross B. So we can literally think of f as being a subset of A cross B, which makes it much nicer to precisely define what a function is. A function is literally a subset of the Cartesian product between the domain and the codomain of the function. So now, of course, all functions need a consistency rule, right? The old input-output interpretation of the consistency rule is you can't have two outputs from the same input. What is that going to look like for ordered pairs? Well, it means you can't have two different pairs with the same x-coordinate. Because if you did, they'd have the same x-coordinate, but they'd have different y-coordinates. The same x-coordinate, same input, two different outputs for that x-coordinate, two outputs for the same input. So now that allows us to give a formal definition for a function. So let A and B be sets. A function f from A to B is now a set. This looks a little bit weird, but we'll see how it works down below. It's literally a subset of the Cartesian product A cross B, such that every ordered pair has a different x-coordinate. Right? Because if they had two pairs had the same x-coordinate, we saw that violates the consistency rule. So here are some examples of functions defined as ordered pairs. Well, functions, I'll tell you, one of these is not going to be a function. Let's see. So we're going to define the function f, or potential function f, as a set of ordered pairs. And here's how we're going to do it, right? We have 1, 2, 3, we have 4 ordered pairs. Each of them has, as an x-coordinate, something in the domain. The domain for both functions is A, B, the set containing A, B, C, and D. And the y-coordinate is going to be something from the codomain. So here, your codomain is the set containing 1, 2, 3, and 4 for both functions. So for f, you have A gets paired with 4, B gets paired with 2, C gets paired with 1, and D gets paired with 2. And f is literally that set. So how would we interpret this set of ordered pairs as a function as we did with some of the other models? So and by the way, here's G as well, also defined as a set of ordered pairs. So for instance, what if, C is in the domain, I should be able to tell you what f of c is just by looking at f as a set of ordered pairs. Well, what I'm going to do is I'm going to look at that set of ordered pairs. I'm going to look for c as an x-coordinate, and if I look at that third one, yeah, I do get c as an x-coordinate, right? I get c as an x-coordinate, 1 as a y-coordinate. That is a member of the set f, right? And what that means is c is the input, 1 is the output, so f of c is equal to 1. And similarly, f of a is equal to 4, f of b is equal to 2, and f of d is also equal to 2. And that all works out fine, right? Every ordered pair has a different x-coordinate, so you don't have two x-coordinates or the same x-coordinate with two different y-coordinates. Now, we're going to have some issues with G, though, right? Because if we want to know what G of A is, we've got to look for an ordered pair that has A as an x-coordinate. And if you look at that first ordered pair in G, that's A2, that says that A is the input, 2 is the output, which means that G of A is equal to 2. So that's fine. Except if you look at the last ordered pair, that also has A as an x-coordinate, but it has 1 as your y-coordinate, which means A is the input, 1 is the output, and so G of A is equal to 1. And so you look at those last two lines, you have G of A equal to 2, G of A equals 1. That is completely contradictory, so you can't have that. So that means that G is not a function. And I shouldn't say you can't have that. You can't have that and still have G be a function. So G is a perfectly nice, what we will eventually call a relation, but it's not a function. All right, so now you are ready to work on the remaining activities for composition of functions that is on the PDF file included with this video.